So again, what makes all of this calculation work? This only works because my first derivative of the function was bounded above by some number capital M, excuse me. And under my assumption, the second derivative should be bounded below by some number negative m as well. How do I know that's going to be true? Well, if I'm looking on a finite interval, then I know that any continuous function is going to have a very maximum function, a global maximum, if you will, a minimum value. So I'll just pick the bound, which is the biggest. So all of this calculation tells me that my remainder term does indeed have to be bounded by that strange looking formula from the theorem. So this is the place where that formula comes from. This is doing it for the degree 1 Taylor remainder, but we could do this for any number of derivatives. Now, something that makes this a bit more useful is the fact that the factorial function grows faster than the nth power function. So I don't care what number x is. In the limit, as n goes to infinity, x to the power n divided by n factorial will go to 0 every single time. How do I know that? Well, I know that the power series x to the nth power divided by n factorial converges. I used the ratio test to prove that. And if a power series converges, then the individual summands must be going to 0. That is required for convergence. So let us actually figure out whether or not the exponential function is equal to its power series. So once again, every function which has infinitely many derivatives, or you might say every function which is infinitely differentiable, has a Taylor series or a Maclaurin series. The question is that Taylor series equal to the original function? In order to establish that, we're going to use Taylor's inequality. So we need to pick an interval. Here, we're going to center at 0, and we're going to look at all coordinates up to distance d away from 0. Well, I know the n plus first derivative of the exponential function. That's just e to the power x again. And that must be less than or equal to e to the power d, since the exponential function is increasing. This estimate for the remainder takes the following formula. The nth remainder from my Taylor polynomial, which is trying to approximate the exponential function, is going to be less than or equal to e to the power d, which is my derivative here, divided by n plus 1 factorial times x to the power n plus 1 factorial. Well, what happens to that remainder as I take n going to infinity? So as n goes to infinity, well, this e to the power d is just a constant. It's not changing. So I can pull that out to the front of the limit. And this limit, I've got x to a power. I'm dividing by the factorial of that power. The limit's going to go to 0. So my remainder term also has to go to 0. Why is that? The magnitude of a remainder function is going to 0. So from above, I've got a limit going to 0. From below, I've got a limit going to 0. And we catch it with the squeeze theorem. All of this calculation is going towards proving whether or not the exponential function is equal to this power series that we built up from taking derivatives of the exponential function. And the answer is yes. The exponential function is, in fact, equal to a power series.